Hey, what's up, nerds? Today we are going to be talking about finding asymptotes of rational functions. One more time, rational just means fractions. So I know, my three greatest fears are being buried alive, falling out of an airplane, and functions. Yeah, fractions and functions together, rational functions. So we are going to talk about asymptotes today. Make sure your mom doesn't hear you say that word, otherwise she's going to think you're swearing. And you know moms, they don't stand for that stuff. I've got good news for you though. Our objective today, you need to learn about 3 types of asymptotes and how to find them. We're cutting that down to 2 types of asymptotes. And we're doing that because your homework just doesn't have slant asymptotes. Those things are not on there. What is on there are horizontal asymptotes. And guess the other one. Can you guess? I bet you can't guess. Vertical. There's no way you guessed that, right? I'm pretty sure you didn't guess that. All right. So you don't need to know about these slant ones. They're pretty cool. We might actually learn about them a little bit later. Maybe if you're lucky, you'll get to do some slant stuff. But for today, we are going to just stick to horizontal and vertical. All right, let's talk about your vocabulary before we get too lost in the sauce, you know what I mean? Before we dive into these asymptotes. We need to talk about the words I'm going to say so that you know what I'm talking about. All right, I keep saying asymptote, and your mom keeps yelling at you because she hears it, and she's like, I thought you were in school. You can't be listening to language like that. You go, no, Mom, it's my math teacher. I'm sorry. He's kind of weird. An asymptote is an invisible line that the function continuously approaches. This means it gets closer and closer and closer and closer, but never quite gets there. This is like you thinking about texting your crush. You're like, oh my God, should I do it? Should I send this? And then you like type it out on whatever it is kids use to type nowadays. And then you like take a screenshot of it and you send it to your best friend and you have them proofread it for you. And you're like, oh my gosh, does this sound too cringy? Like, do you think they're going to like this? And then they're like, yeah, just send it. And then you're like, all right, I'm going to send it. And then you don't. That's the important part. And then you don't. It gets really, really, really close, right? Like your finger's like a millimeter from the send button. But then you don't. It never gets there. Okay? That's the important part. Gets really close to an invisible line, never touches. That's all you gotta know. Degree, this is an old favorite, of course. I know you know this one. This is determined by the largest exponent of a polynomial. So if you have something like x to the 4th plus 7x squared minus 7x plus 15, the degree is 4. It's just that big exponent. Cool. And then once more for the people in the back, undefined. This happens when your denominator equals 0. That's going to be super important for one of our types of asymptotes today. These are also the x values where restrictions happen. So you guys already know how to find restrictions. I taught you super duper well how to do that in the last video. So now we're going to do it again to find one of our asymptotes. All right, so let's go look at the easy asymptotes first, our vertical ones. So vertical ones happen when the function is undefined. Okay. So the places where our function is undefined at are the places that we have restrictions. And to find our restrictions, all we have to do is set the denominator equal to 0. So if we set x minus 5 equal to 0, and x plus 1 equal to 0. We get x does not equal 5 and x does not equal negative 1 as our restrictions. These are also telling us where our vertical asymptotes are. I've already graphed this function for you using Desmos. So x equals 1. Remember, when x is 1, negative 1, that's like negative 1, 2, negative 1, 3, negative 1, negative 1. The x value of the ordered pair stays negative 1 forever, and then the y changes. That's what this looks like. So if we go to negative 1, 2, -1, 3, -1, -1. These are just a bunch of vertical points right there. So x equals -1 is a vertical line, and you can see our graph curves up. It's like, wait, I don't want to run into that wall, and it keeps going, and it goes straight up, and on this side it goes straight down. It gets closer and closer, but never touches. This is our vertical asymptote. This is our vertical asymptote. Technically the asymptote is x equals -1. It's that line. The other vertical asymptote happens here at 5, because that's where our other restriction is. So these are the equations of our asymptotes. These are the restrictions. Very similar. You find them the same way. They happen in the same spot. But this one is saying, this is the line that I don't touch, and these are the x's you're not allowed to plug into this function. Subtle difference, but, you know, if you're going to college, you should be aware. All right, one more for the people in back. To find vertical asymptotes, set the bottom equal to 0, solve for x, it's those numbers. Okay. Now we have to talk about our second type of asymptote, which are horizontal asymptotes. So let's start by talking about vertical asymptotes just to drill it into your heads. If I set these equal to 0, I'm going to get x does not equal +2, and x does not equal -1. If we look at this graph, these are the same graph. This one's just zoomed in, and this one's zoomed out. You see how this one only goes to 4, and this one goes to way more than 10? Same graph, just zoomed out. Okay. So if we look at x equals 2 and x equals -1, x equals 2 is right here, and x equals -1 is right there. You can see our vertical asymptotes, and it's not as obvious here because it's all zoomed in, but x equals 2 is right there, and x equals -1 is right there. Okay, so there's our vertical ones. Now you're gonna say, Barton, the title says horizontal asymptotes. Why'd you find me the vertical ones? I'm just refreshing, kids, so you remember what's going on from the last slide. Okay, we'll just put these over here so we don't forget them, and we'll put them there. All right, so to find our horizontal asymptotes, we need to look at the degrees of these polynomials. Okay, the degree here is 2, and the degree here is not obvious because it's factored. So we'll multiply it back together, and then I'll tell you a trick. So x times x is x squared, x times 1 is +x, -2 times x is -2x, and -2 times 1 is -2. Combine your like terms. This is x squared minus x minus 2. Cool? You guys okay with that? Cool. So if we look at our degrees of the top and the bottom, they are the exact same. That's one type of horizontal asymptote. There's actually, you know, that's all there are for this one. So when they are the same, this one can't really overpower this one or anything. They're even. So the way we find the horizontal asymptote is we just look at the coefficients of the x squared terms. The coefficient here is 1. The coefficient here is also 1. The ratio of the coefficients is where the asymptote is at. Let me say that. Let's write that down. The ratio, that means the fraction, so top over bottom. So our ratio here equals 1. It's 1 over 1. The ratio of the coefficients is where the horizontal asymptote is located. Okay. And the way we get the equation, because that's what it's going to ask you for on your homework, is it's always going to be y equals the ratio. So this one is going to be y equals 1 is our horizontal asymptote. So now let's go look and see what that means. Just like we said x equals a number is a whole bunch of repeated x values. Y equals a number is the same thing. So this is 0, 1, 1, 1, 2, 1, 3, 1, and so on. So it would be this point, this point, this point, this point. It's this horizontal line at 1. So it's not super obvious on the top graph that these graphs keep going to 1. So if we zoom out, I have the same blue horizontal line at y equals 1. And then these red ones, you can see they taper off and they get really close to the blue one. So that is how you find your horizontal asymptotes. Let's go look at one more example just to see what's going on. All right. So here, these are going to be the same degree because you have 1, 2 x's. So when you multiply them together, you're going to get x squared. And pro teacher tip, all you have to do is this term times this term to get the coefficient that you want. All the stuff after it is not important for the asymptotes. So x times x is x squared, and then you would have minus x plus 4x, so you have a 3x minus 4 here, but it doesn't matter because all we care about is that coefficient. So our ratio of our top coefficient over our bottom coefficient here is 3. It's 3 over 1. So that is where our horizontal asymptote is going to be. So if we look at our graph, here's the graph of this function. Right here at 3, you can see our horizontal asymptote. And again, if you zoom out, you can see that it takes a while to taper off, but you can still see it. We can also see our vertical asymptotes here. Solve both of these for x when you set it equal to 0. X equals negative 4. Right there at negative 4, we have a vertical asymptote. And then solve this one, x equals 1. Right here at x equals 1 is our other vertical asymptote. Okay. Pardon me. Sorry, my dogs are, losing their mind. But, you're going to have to forgive them. They're insane dogs. They don't know any better. They can't even do math. So you're going to have to forgive them. All right. So we have our vertical asymptotes. We're done with this one. Sweet. Okay. All right. Last example. You're going to say, Mr. Barton, what if the bottom exponent is bigger than the top exponent? Well, this is going to give you a super easy asymptote. You don't even have to do the rest of the problem. Or rather, you don't have to look at ratios and stuff. If the bottom asymptote is bigger, let's write this down. If the bottom, not asymptote, degree. Bottom degree is bigger, the horizontal asymptote is at y equals 0. It'll always be the x-axis. And we'll talk about that y after I point at these graphs a little more. So obviously you can't see it here. If you look at this function, because of this 20 is kind of big compared to the other numbers, you can just barely see that corner and barely see this corner with how zoomed in it is. But if we zoom out, you can see once you get closer to like 40 or negative 40, it kind of levels off at 0. So the reason this always happens, this could be 100, it could be a billion. I don't know what there you go. It could be that number. It doesn't matter what this number is. It will never overpower the x squared. So let's look at this as an example, and let's just plug in some points to demonstrate what I'm talking about here. All right, so x. If we plug in, I'm going to do a bunch of rounding here just to make my life easy. Let's plug in 1, 10, 100, and we'll try 1,000, but I don't know if I can count that high. So if I plug in 1, this is 20 over 1 minus 1 is 0. Oops, that's our asymptote. There's a vertical asymptote. 1 doesn't work. Let's pick 2. So this is 40 over 3. All right, because 2 squared is 4 minus 1 is 3. So that's, about 12, let's say. Is it? I don't know. I don't care that much. It's about 12, sure. Okay, let's plug in 10. So 20 times 10 is 200 over 99. That's about 2. Okay, you can see this number is going way farther down. The top is still bigger, but the bottom is catching up. This 20 just gives the top of the fraction a big head start. So if the top number of a fraction is big compared to the smaller bottom one, you'll get a big number, right? Like 20 over 1 is 20, but 20 over 20 is only 1. It's a lot smaller, right? So because this is squared, the bottom will eventually catch up to the top. So let's plug in 100. 20 times 100 is 2,000, but 100 squared is, 2,000 is 10,000. So minus 1. This is 9,999. So this is about 1/5. The bottom has by this time caught way up, and this is getting really small. This is the same as 0.2. We're in the decimals now. We're not very far above 0. If I plug in 1,000, this would be 20,000 over 999,999. Shout out to my Final Fantasy fans. I don't know what this is. This is like 1 over 20 or 1 over 50, something like that. This is like 0.02. It's super tiny. So because of this squared right here, the bottom just always catches up, no matter how big this is. Sure, if this were a billion, it could fight it off for a long time, right? We might have to plug in a million here, but you know, this squaring just overpowers it by so much. Eventually, if you plug in a trillion, a quadrillion, a septillion, you know, a nonillion, Graham's number, the bottom just gets so much bigger because of the squared. So a tiny number divided by a really big number is about 0 if, you know, we plug in big enough numbers. So let's summarize that for the people who kind of dozed off because math got too cool for them. I'll just refer you to this. Whoa, what happened there? If the bottom degree is bigger than the horizontal asymptote equals 0 every single time. So f of x equals a billion x over x squared. The horizontal asymptote is 0, even though this is a big number. We don't care because this is bigger than this. Y equals 0 is the horizontal asymptote. All right, hopefully I didn't belabor the point too much, but the video is 18 minutes now, so, you know, your boy's got to belabor a little bit. If you need help, make sure you ask me in the WebEx or band or email me. Cool. Have a good day.